Okay, so in this slide, I tried to put in a GIF image so it would actually move like a wave. You guys get the gist. So light emanating off the object moves in waves. Now, we describe the waves using the following terms: wavelength and amplitude. So the next slide is going to talk about that in a little bit more detail. But when we talk about light, light is measured in nanometers. So basically, when we talk about light being 400 nanometers, the peaks of the wave, so here, 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 are 400 nanometers apart. So here's 1, 2, 3, 4. So shorter wavelengths are perceived by humans as violet or blue, like think of a rainbow, which we're going to look at in a minute. Longer wavelengths, so there's a bigger space between here, is perceived by humans as red. So shorter is more like violet or blue, wider is red. Now, we're going to see in a minute that we only see a fraction of the light that is produced by the sun. Such a tiny amount. So listen to this. We don't see gamma rays, X-rays, ultraviolet rays, infrared rays. I mean, we can see infrared when we put on those special glasses. Microwaves and radio waves are outside the range of wavelengths the human eye can detect. These forms of energy have features that make them less desirable stimuli for a sensory system. Shorter wavelengths, such as ultraviolet rays, so then that would be narrower here, are typically absorbed by the ozone layer of the Earth's atmosphere, leaving little energy left over for most organisms to sense. Nonetheless, some creatures, including bees, are able to see parts of the ultraviolet spectrum. Longer wavelengths, so remember this big old space here, such as microwaves, tend to penetrate objects rather than reflect back from them, a feature that is valuable in cooking but not in vision. So now, I'm going to also talk with you about the different features of wavelength and amplitude, and then we are going to talk about the very small amount that we can actually see of the available light from the sun.